So for one final example of redox reactions, I'd figured I'd share to you one of my projects in grad school. Here we were trying to design thermochromic glazings of smart windows, or air coat smart windows. And when I say smart windows, the vision here is basically for these thermochromic rather, glazings on windows to let in heat at your home during the winter, okay, and to reflect it off during the summer, which basically saves you money on heating and cooling, okay. Now there are various coatings for windows already available in the market, such as electrochromic coatings, okay, and you have to, however, flick a switch in order to block off heat from the outside. So sure, that actually helps with mitigating or controlling the temperature of your room more efficiently, but you still need to power on those electrochromic coatings. For VO2 or vanadium 4 oxide, we can actually use it as a thermochromic glazing or coating. And by thermochromic, that just means it changes in state at a different temperature. Okay, so for electrochromic, that's as a response of a change in electricity. Okay, but for VO2, what we envisioned for this material to work was when it's hot outside, the smart window will actually, I guess, adapt to a crystal structure in which it blocks off heat from the outside, and when it's cold outside, it adapts into a crystal structure which takes in heat from the outside. And when I say crystal structure, that's actually a little bit complicated from what we've seen so far. Crystal structures are long-range networks of atoms in a solid. We may or may not discuss that for this course. But to those curious, the thermochromic response from VO2 is as a response, or as an effect rather, of its metal to insulator phase transition. Okay, and this occurs as a phase transition from the monoclinic phase, okay, to the tetragonal phase. We're not going to discuss that in greater detail, but just in case you're curious. And 67 degrees is still too high, so what we did was actually to introduce boron atoms. Now for the actual chemistry, this is what we do to actually produce VO2, or at least one of the ways. Okay, it's a constant pressure reaction, okay, and the precursor is vanadium 5 oxide, okay, and it's being reduced. So let's see if indeed vanadium 5 oxide is being reduced here. Okay, so let's rewrite this equation on this clean slide. So 8V2O5, okay, plus C3H6O. This is actually acetone, okay, and then 16VO2 plus CO2. That's 3CO2 actually, and then plus 3H2O. Okay, as always, we start first with hard rules. We can see a lot of oxygens here. In fact, we see it for everything. So let's assign oxygens first. Okay, so this one is -2, and since you have 5 of them, so -2 times 5, the total contribution here of oxygen is -10. Okay, you have 1 oxygen here, that's -2. Okay, you have here 2 oxygens, which are -2 each, so -2 times 2 is equal to -4. Okay, same thing with this one in carbon dioxide, and then just 1 for water. Okay, and then the next rule that we can assign will be hydrogens, and then after that I think we should be ready to go. Okay, so for hydrogens here, you have +1 for each hydrogen. Remember, that's a hard rule for hydrogen, except if it's a hydride. Okay, so that's +1 times 6 is equal to +6. Okay, and then this carbon is, well, my bad, we're not actually going to look at that carbon yet. And then this hydrogen, rather, is +1 times 2 is equal to +2. Okay, now, so you can see, this actually, well, we don't really need to do anything with that one yet, but we've just proven here that the oxidation states actually add up to 0. Okay, now we can fill in the blanks of whatever's missing. Okay, if this is -4 and we only have one carbon, then this carbon should be +4. Okay, now this vanadium should be +4 as well. Okay, because right now you have -4 from all the oxygens. And then let's skip first to this vanadium. So you have 2 vanadium atoms and you need a +10 to have a 0 charge. Okay, or a 0, yeah, sum of oxidation states. So this one should be +10 divided by 2 is equal to +5. Okay, and then now let's work at this other carbon. So we have here -2 and +6, which is just equal to +4. Okay, so therefore this carbon, since there's 3 of them, should be -4/3. Okay, once again, it's okay to have fractions as oxidation states. Okay, we notice that vanadium and vanadium 205 or V2O5 actually is being reduced. Okay, so here V in V2O5 is reduced. Okay, and therefore V2O5 is the oxidizing agent. Okay, and then here we see that the carbon in acetone is actually being oxidized from negative to positive. So C in C3H6O is oxidized, and therefore acetone is the reducing agent. All right, that's it.